Hello students, welcome back. In this video we are going through Chapter 4, Section 4, Counting. No, this isn't counting as in 1, 2, 3, 4, 5. We are counting in the context of we want to know how many different possible outcomes we may have given a scenario. So this section requires a greater use of formula than we have been doing in the past. So it's a little bit more of plugging and chugging or using technology. But we are going to talk about 5 different methods for how to determine how many possible outcomes a variety of situations may have. Okay, so first we will look at the multiplication counting rule. Okay, so the multiplication counting rule says, for a sequence of events in which the first can occur in 1 ways, the second can occur in 2 ways, the third in 3 ways, and so on, the number of total outcomes is just going to be all those number of ways multiplied by each other, and 1, and 2, and 3, go on and on forever. So let's just look at a very quick example. So a hacker is trying to guess a passcode. Say you leave your iPhone in the classroom and someone grabs it and, oh, it's password protected. There's a 4-digit code. Well, how many possible passcodes can you have? Everyone knows that there's, well, you can have it as a 4-digit passcode or a 6. We'll say they have a 4-digit one. You can do obviously 0000, 9999, and any number in between. So how many different possible passcodes are there? Well, given that all the guesses had the same chance of being correct, what is the probability of guessing the correct passcode on the first attempt? Pretty slim chances, as you know, just fiddling with your friend's passcode. But let's look at it. Each of the 4 digits has 10 possibilities. So the first digit, there's a 1 in 10 chance you'll get it correct. 0 through 9. 0, 1, 2, 3, 4, 5, 6, 7, 9, there's 10. The second digit also has 10 different possibilities. The third digit, 10 possibilities. And the fourth digit, 10 possibilities. Each of the 4 digits can be 0 through 9. So since there are 4 digits, we have N1, N2, N3, and N4. And since each of these n's have 10 possible passcodes, we say 10 times 10 times 10 times 10. So there are 10,000 different possible passcodes that an iPhone can have if there's 4 digits. So because we're saying that all the passcodes are equally likely to happen, the probability of getting the correct passcode on the first try is 1 over 10,000, or 0.0001. In practice, you probably know that most of you guys' passcodes is like your birthday or something, but we're ignoring that. So there's a 1 in 10,000 chance of getting it right. There's 10,000 combinations. And this also makes sense, just thinking of a 4-digit passcode as randomly choosing a number between 0 and 9,999. There are 10,000 numbers between 0000 and 9999. You know, there's 0000, 0001, 0002, and that can go on up until 9999. So likewise, there are 10,000 possible combinations. So that's the multiplication counting rule. Now let's look at the factorial rule. So factorial rule says that the number of different arrangements, order matters, of n different terms when all n of them are selected is n exclamation mark. Oh, what does the exclamation mark mean? That's just the way we determine factorial. So factorial is saying you have a select number of possibilities and you can't use each one more than 1 time. So once you use it, it's gone. So the first time you might have, say, 5 possible things to choose from. And then once you choose the first one, now there's 4 left. Then there's 3. Then there's 2. Then there's 1. So factorial symbol is exclamation mark, denotes the product of decreasing positive whole numbers. And by definition, we just say that 0 exclamation mark is equal to 1. Don't worry too much about that. So the factorial rule is based on the principle that the first item may be selected n different ways. The selected one may be selected n minus 1 ways, and so on. Then it'd be n minus 2 ways, however many possible choices you have left. Uh-oh. Okay, now that that crisis was averted, let's move on. So let's look at an example that has the factorial rule in it. So a statistics researcher must personally visit the presidents of let's see, Gallup, Nielsen, Harris, Pew, and Zogby Polling Company. So we have 1, 2, 3, 4, 5 different places that he is or she is visiting. So part A wants to know how many different travel itineraries are possible. Well, this is not going to be a multiplication counting rule, because that would tell me that each time I'm visiting a place, there are 5 possible places to choose from. But in this, it isn't so. Say the first time we visit a place, well, how many choices do we have? We have 1, 2, 3, we have 5 places to choose from. So let's say we choose Gallup, okay? So now, for our next destination, how many places do we have to choose from? 1, 2, 3, 4. Then we choose, I don't know, Pew. And then what do we have left? 3. Then 2. Then 1. So you guys remember the little branches they used to make back in the day, where you have, first you have 5 choices, and each of those extend to 4 more choices, and 3, then 2, then 1. And we're just multiplying those all out. 5 times 4 times 3 times 2 times 1. Now let's see that written out. So for those 5 different places, the number of travel itineraries is going to be 5 factorial, or 5 times 4 times 3 times 2 times 1. So if you do the multiplication counting rule, you just have to note that you are reducing the number of possible places to go to by 1 each time. So 5 times 4 times 3 times 2 times 1. Part B is asking if the itinerary is randomly selected, what is the probability that the presidents are visited in order from youngest to oldest? And you might say, well, how the heck am I supposed to know? I don't know what their ages are. But what this problem is really trying to get you to see is that how many of those 120 itineraries are going to be exactly in the right order from youngest to oldest? Well, there's only one possibility. I don't need to know which one that is. I just have to know that there's only one possible way to have them be from youngest to oldest. So it's going to be 1 over 120 as that probability. So how do we do that using technology? Well, I don't want to just have you guys do the math by doing 5 times 4 times 3 times 2 times 1. I would rather you know how to use it using the TI-84. So I pulled up my handy dandy TI-84. So let's look at the directions. Hit the number you would like the factorial of. Then hit math, move over to PBR for, you guessed it, probability, and then select 4. So let's go back to our TI-84. So hit the number we want to get the factorial of. So 5. Then go to math over here. Go over to the right where we get to this right here, and we want to know for the factorial. So that's 4 right there. Hit enter again, and there's your 120 number. Let's go back to the slideshow. Okay, so that was, now we did multiplication counting rule, and then we did factorial rule. Next, we are doing permutations and combinations. I know you guys have done this before, but let's go over it again. We are assuming that this is your first exposure to this. So now we are looking at permutations and combinations, and they are pretty similar in a lot of ways, except the big difference is in one, order counts, and the other, the order of them does not count. So permutations are items arranged in a way in which different sequences of the same items are counted separately. So what do I mean by that? So say you have the letter arrangements ABC, ACB, BAC, BCA, CAB, CBA. They are all counted as 6 separate outcomes. ABC and ACB are 2 separate things. When we do combinations, we'll find that they are counted as the same thing. So let's look at an example. Well, first we'll talk about combinations. Combinations that these all have the same 3 letters, just arranged differently, they would be considered the same combination. So different permutations, same combinations. So remember, permutations, positions, where position the alliteration reminds us that with permutations, the position of the items make a difference. Position matters. Permutation, position. Combinations, you think of like a committee. Members of committee, well, if you rearrange the names it's still the same committee. Order doesn't count. If there's a council of 5 people and I read Matthew, Mark, Luke, John, and then Jim, or if I read them in any different order, it's still the same committee. So combinations, the committee, the order does not matter. It's all the same outcome. So let's look at the rules for them, the equations that follow. So when n different items are available, and r of them are selected without replacement, meaning once you use somebody, you can't get that outcome again, the number of different permutations is given by this formula right here. It's n factorial divided by n minus r factorial. So let's look at an example. You guys might have been to Monmouth County Racetrack or a place where there's horse races. But if you haven't, the equation's still a good one. Or the example is still a good one, I mean. In a horse race, a trifecta bet is won by correctly selecting the horses that finish in first and second and third place, and you must select them in the correct order. So the Kentucky Derby has 19 horses running. So there's 19 horses in the race, and you want to correctly guess who gets first place, who gets second place, and who gets third place. So how many different trifecta bets are possible? Okay, so this is going to be a permutation or a combination one. And you have to ask yourself, does order matter? Yes, order matters, because if I get first, second, and third place correct, but if I got third place, first place, second place, the same 3 horses, different order, I'd be wrong. So it's a permutation. So with 19 horses available, we must select 3 of them without replacement, so r is 3, and the equation is as follows. 19 factorial divided by 19 minus 3, or 16 factorial, equals 5,814. So there's that many possibilities, and then we'll go to part B now. So part B says, if a bettor randomly selects 3 of those horses for a trifecta, what is the probability of winning? And we are assuming that each horse has the same chance of winning, just to make the equations easier. Obviously, a better horse with better odds is going to have a better chance, but we're just ignoring that. So we are just going to say that there are 1 over 5,814 chances of getting it correct if you have no reason to believe that any horse has any better odds than any other one. So how do we do that using technology? I use a TI-84 for these. So first you determine your n and your r value for when you want to do a permutation using the TI-84. So determine your n and r. Then you have to type in your n value, and then very similar steps to when we did factorial, but instead of hitting 4 for the exclamation mark, now we're hitting 2 for the n, permutation, r. Then just hit enter. Let me quickly show you how to do that. So I'll go back up to here. So we have to type in the n first. So that was 19. Hit math. Go over to PRB for probability. 2 for permutations. And then I'm saying I'm choosing 3 of those 19. 5,814. Same value we got from here. 5,814. 5,814. Okay. Now we're going to talk about a different type of permutation. So we're saying the permutation rule when some items are identical to another item. So the number of different permutations when n items are available and all n of them are selected without replacement, but some of them are identical to others. It is found by this equation, where n factorial is n1 factorial times n2 factorial, so on, so on. So let's go to an example. This is a little bit hard to explain, I see, without looking at an example. So when designing surveys, pollsters sometimes repeat a question to see if a subject is kind of thoughtlessly providing answers just to finish quickly. So for one particular survey with 10 questions, 2 of the questions are identical to each other, and 3 other questions are also identical to each other. So for this survey, how many different arrangements are possible? Is it practical to survey enough subjects so that every different possible arrangement is used? Okay. So we have 10 questions with 2 that are identical to each other and 3 that are also identical to each other. And we want to know the number of different permutations. So we're going to use that rule. So we have n factorial, which is, the 10 number right here. We're going to divide it by n of 1, which is the 2, and then the n of 2, which is 3, which gives us 302,400 possible permutations right here. So there are that many different arrangements of the 10 questions. Now we'll talk about combinations. So the rule for that is as follows. When we have n different items available, are selected without replacement, and the number of different combinations does not matter, like the committee, we have this equation right here. N factorial divided by n minus r factorial multiplied by r factorial. So we'll look at a lottery game. So in California's 5 lottery game, winning the jackpot requires that you select 5 different numbers from 1 through 39, and the same 5 numbers must be drawn in the lottery. So you guys have played probably the Jersey Cash 5. You choose 5 numbers, then they draw them, and then you have to get all 5 correct to win the jackpot. The winning numbers can be drawn in any order, so order does not make a difference. Since order does not make a difference, we're dealing with combinations. So how many different lottery tickets are possible? How many different ways can you get that? So there are n equals 39 different ways available. We must select 5 without replacement, and because order does not matter, we're using a combination. So we're just going to plug it into our equation. 39 factorial divided by 39 minus 5 factorial multiplied by 5 factorial gives us this right here. We can also use that using technology. I'll get to that in a minute. So then when we are saying if you randomly selected a 5-number combination, you do like the quick pick option, your chances of winning are going to be 1 over that. So this is I love how the book finds the need to include this. Typical lotteries rely on the fact that people rarely know the value of probability and have no realistic sense for how small the probability actually is. So they're saying the lottery is a fool's man's bet. I don't know. So let's just show you how to do that with technology. So let me go back to my handy dandy calculator. And it's a very similar process. We are going to determine n and r, type in n, go here to the same screen, and now we're just going to do 3. Then type in the r value, and then we're golden. So 39, math, go over to probability. We're doing combinations, and we're choosing 5. And that's it. That's how we get the answer. And that concludes Chapter 4. Any questions, let me know.